September 23, 1944, the proving grounds of Aberdeen, Maryland. The autumn sun casts long shadows across the testing range, and the smell of diesel exhaust mingles with the earthy scent of churned mud and crushed grass. American engineers stand in a semicircle around a massive steel beast, their clipboards and measuring tools held at the ready. The tank before them is a Panther Ausf, G. Panzerkampfwagen Vieh, captured intact during the fighting in France just weeks earlier. Its sloped armor gleams dully in the afternoon light, the German crosses hastily painted over with white stars. The engine idles with a deep mechanical rumble that seems to vibrate through the ground itself. One engineer, a young lieutenant from Detroit named Robert Fisher, places his hand against the final drive housing at the rear of the tank. The metal is already hot, almost uncomfortably so, and the vehicle has been running for less than 20 minutes. He pulls his hand back and makes a notation on his pad. Another engineer kneels beside the massive steel wheel, examining the bolts that secure the final drive to the hull. He counts them, 8 bolts, each one straining against forces that seem to exceed their capacity. He runs his finger along a hairline crack already forming in the housing. The tank has traveled barely 30 miles on American soil, and already the evidence is emerging. This machine, this symbol of German engineering supremacy that had terrorized Allied forces from Kursk to Normandy, carried within its mechanical heart a flaw so fundamental that it would reshape American understanding of their enemy, not as invincible supermen, but as engineers and soldiers trapped by their own ambitions, fighting a war with machines designed beyond the capacity of their industry to sustain. The Panther had entered American consciousness as a nightmare made steel. Reports from the battlefields of Europe spoke of it in tones of grudging respect and genuine fear. It first appeared in July 1943 at the Battle of Kursk, where German forces launched the largest tank offensive in history against Soviet defenses. The Panther was meant to be the answer to the Soviet T-34, a medium tank that could dominate the battlefield with speed, firepower, and armor protection that exceeded anything in the German arsenal at the time. The designers at MAN, Maschinenbau Augsburg-Nürnberg, created something extraordinary, a tank with sloped frontal armor up to 80 millimeters thick, angled at 55 degrees to maximize deflection. It mounted the legendary 75mm KWK 42L70 gun, capable of penetrating any Allied tank at ranges exceeding a mile. It weighed 45 tons, yet could reach speeds of 29 miles per hour on roads. To American tankers who first encountered Panthers in Normandy, the vehicle seemed almost invulnerable. Sherman tanks, the backbone of American armored forces, found their 75mm shells bouncing harmlessly off the Panther's glacis plate. The Germans could engage from distances where American guns were ineffective, picking off Shermans with methodical precision. Intelligence reports compiled by Allied headquarters in the summer of 1944 painted a grim picture. One after-action report from the British 7th Armored Division described an engagement near Villers-Bocage. Enemy Panther tanks engaged our Cromwells at approximately 1,200 yards. All hits on frontal armor failed to penetrate. Enemy fire was devastatingly accurate. 5 of our tanks destroyed before contact was broken. American tank commanders developed desperate tactics, flanking maneuvers, close-range ambushes, coordination with tank destroyers, and air support. The standard doctrine became brutal in its simplicity. It took 5 Shermans to kill 1 Panther, and 4 of those Shermans would burn in the process. The crews knew this. They climbed into their tanks each morning with the knowledge that German armor was superior in nearly every measurable way, and that survival depended on numbers, luck, and the willingness to accept catastrophic losses. The psychological impact was profound. American tankers began calling their Shermans Ronsons, after the cigarette lighter advertised to light first time, every time. The nickname was Dark Humor, masking genuine terror. When a Sherman was penetrated, and Panthers could penetrate a Sherman's armor from virtually any angle, the internal ammunition storage often detonated, killing the crew instantly or trapping them in an inferno. Tankers learned to bail out at the first impact, abandoning their vehicles rather than waiting for the second shot. Some crews refused to close their hatches fully, preferring to risk small arms fire rather than be sealed inside a potential crematorium. The reports reached Washington, and senior commanders recognized a crisis of morale brewing among armored forces. Something had to be done, if not to match the Panthers' capabilities, then at least to understand them. The opportunity came in August 1944 during the chaotic fighting around the Falaise Pocket. A Panther from the 2nd Panzer Division was disabled by a lucky shot from a 90mm anti-aircraft gun pressed into anti-tank service. The crew abandoned the vehicle, which was subsequently captured by the American 2nd Armored Division. Unlike most captured Panthers, which were destroyed by their crews or damaged beyond repair, this one was largely intact. The final drive had been damaged in the engagement, and the tank could not move under its own power, but the hull and turret were sound. Orders came down from SHAEF headquarters. The vehicle was to be recovered and shipped to the United States for detailed examination. Engineers and maintenance crews worked through the night to prepare it for transport. It was loaded onto a Liberty ship in Cherbourg and sailed across the Atlantic, arriving in New York Harbor in early September before being transported by rail to the Aberdeen Proving Ground in Maryland, where the U.S. Army tested and evaluated military equipment. The testing program that began that autumn was exhaustive and methodical. American engineers approached the Panther with a mixture of professional curiosity and personal investment. Many had friends or brothers serving in armored units in Europe. They understood that every weakness discovered, every vulnerability documented, could be translated into tactical doctrine that might save American lives. The Panther was measured, weighed, photographed, and disassembled piece by piece. Engineers examined the armor composition, the welding quality, the gun stabilization, the optical sights, the transmission design, the suspension system. They test-fired the main gun at various ranges against mock-ups of American tanks. They drove the Panther through obstacle courses, across rough terrain, through mud and sand. They pushed it to its mechanical limits and documented every failure, every breakdown, every design compromise, and the failures came quickly. The first major issue emerged within days. The Panther's final drive, the gearbox assembly that transmitted power from the engine to the drive sprockets that turned the tracks, began showing signs of severe stress almost immediately. The final drive was located at the front of the tank, one on each side, housed in armored casings that protruded slightly from the hull. During a routine test run across moderate terrain, one of the final drives began making an ominous grinding sound. The engineers stopped the tank and allowed it to cool. When they removed the inspection plate, they found metal shavings and fragments in the gear oil. The gears themselves showed signs of accelerated wear, the teeth beginning to strip and deform. This was after less than 50 miles of operation under controlled conditions, far gentler than combat operations. The engineers were puzzled at first. They examined the design specifications and compared them to the observed stresses. The mathematics told a damning story. The Panther's final drives were essentially borrowed from earlier, lighter German tanks and modified for use in the much heavier Panther. The drives were rated for a vehicle weighing approximately 30 tons. The Panther weighed 45 tons fully loaded, and combat conditions often added several more tons in ammunition, fuel, spare tracks, and crew equipment. The final drives were operating at 50% beyond their designed capacity every hour of every operation. The consequences were inevitable. Under normal combat conditions, Panther final drives failed with regularity. German field reports, captured documents that intelligence officers had been translating confirmed this. Maintenance logs from Panzer divisions showed that final drive failure was the single most common mechanical breakdown in Panther tanks. The average lifespan of a Panther final drive in combat conditions was approximately 150 kilometers, less than 100 miles. When a final drive failed, the tank was immobilized. Unlike engine problems, which might be repaired in the field, final drive replacement required specialized equipment and significant time. The entire drive assembly had to be unbolted from the hull, a process requiring the removal of 8 massive bolts while the tank was supported on jacks, and a replacement unit installed. In combat conditions, this was often impossible. Panthers with failed final drives were abandoned, sometimes with demolition charges to prevent capture, sometimes simply left behind during retreats. German tank recovery teams worked frantically to salvage disabled Panthers, but the sheer number of mechanical failures overwhelmed their capacity. One captured German maintenance report from the 9th Panzer Division, dated July 1944, noted, "Of 27 Panthers rendered non-operational this month, 19 failures attributed to final drive or transmission problems. Spare parts availability remains critical. Recovery assets insufficient to retrieve all disabled vehicles." The American engineers at Aberdeen documented all of this with clinical precision. They measured the torque loads on the final drive gears. They calculated the heat buildup during extended operation. They photographed the wear patterns and metallurgical failures. Lieutenant Fisher, the engineer from Detroit who had first noticed the excessive heat, compiled a detailed report that would later be distributed to armored commanders throughout the European theater. His conclusion was stark. The Panther tank, while superior in firepower and armor protection, suffers from a fundamental mechanical weakness that significantly reduces its operational effectiveness. The final drive system is inadequately designed for the vehicle's weight and performance characteristics. Sustained operation results in predictable failure. Tactical doctrine should emphasize mobility and maneuver to exploit this vulnerability. Enemy Panthers forced to travel long distances or operate across difficult terrain will experience high rates of mechanical breakdown independent of combat damage. The implications rippled through American strategic thinking. The Panther had seemed invincible, but it was not. It was a machine designed by engineers who had been given an impossible task: create a heavy tank with the mobility of a medium tank, mount it with a gun capable of destroying any enemy vehicle, armor it sufficiently to resist all but the most powerful weapons, and do all of this within the constraints of German wartime industrial capacity. Something had to give. The designers had made their choice. They prioritized firepower and protection and accepted reduced mechanical reliability. But reliability in the long calculus of armored warfare was not a secondary consideration. A tank that could not reach the battlefield, that broke down on the march, that had to be abandoned due to mechanical failure rather than enemy action, was worse than useless. It consumed resources, tied up recovery assets, and represented a complete loss of the significant investment in materials, labor, and industrial capacity required to produce it. This realization transformed how American commanders understood the German military. The Wehrmacht had been perceived as a supremely efficient machine, its equipment the product of legendary German engineering excellence. The Panther seemed to confirm this. It looked formidable, it performed brilliantly in certain controlled circumstances, and its reputation preceded it into every engagement. But the reality was more complex and more human. German engineers were not superhuman. They faced the same physics, the same material constraints, the same design trade-offs as their counterparts in every nation, and they were operating under conditions of increasing desperation. By 1943, Germany was fighting a multi-front war against enemies with vastly superior industrial capacity. The Soviet Union was producing tanks in numbers that dwarfed German output. American factories were churning out Shermans at a rate of thousands per month. Germany could not match this quantitatively, so it attempted to compete qualitatively, building tanks so superior in individual capability that they could offset numerical disadvantages. The Panther was the embodiment of this strategy, and its final drive was the symbol of its failure. The weak point was not a simple engineering mistake that could be corrected with better design. It was the inevitable result of trying to do too much with too little. Germany lacked the specialized steel alloys that might have strengthened the final drives without adding prohibitive weight. It lacked the manufacturing capacity to produce entirely new, properly rated final drive assemblies for every Panther. It lacked the time to properly test and refine the design before rushing it into production. Most critically, it lacked the resources to accept that some design requirements were simply incompatible, that a 45-ton tank could not be made as reliable as a 30-ton tank using the same components, and that attempting to do so was engineering hubris. The American engineers understood this because they recognized the same pressures in their own work. The United States had its own design compromises and its own flawed vehicles. The difference was in how those compromises were approached. American doctrine prioritized reliability, maintainability, and mass production over individual superiority. The Sherman tank was not as well armed or as heavily armored as the Panther, but it was mechanically robust, easy to repair, and produced in overwhelming numbers. When a Sherman broke down, replacement parts were readily available, and the vehicle could often be returned to service within hours. When a Sherman was destroyed, another would arrive to replace it within days. The American industrial base could absorb losses that would cripple Germany. This was not a matter of courage or skill. It was mathematics. The final drive of a Panther represented the mathematics of desperation. The final drive of a Sherman represented the mathematics of abundance. As the testing continued through September and into October, the engineers at Aberdeen pushed the captured Panther harder. They wanted to know not just where it failed, but when and how predictably. They ran the tank for extended periods at high speed. They drove it repeatedly over rough ground. They loaded it with additional weight to simulate combat conditions. The final drives continued to deteriorate. By mid-October, one had failed completely, the gears stripped beyond any possibility of repair. The other was making increasingly violent sounds, metal grinding against metal, the internal components beginning their inevitable disintegration. The engineers documented every stage of the failure. They created detailed technical drawings showing the progression of damage. They took metallurgical samples of the failed gears and subjected them to spectroscopic analysis, determining that the steel used was of good quality, but simply insufficient for the applied stresses. The symbolic weight of that final drive, that small, overworked gearbox buried in the front of the tank, grew with each report, each briefing, each tactical update sent to commanders in the field. It became shorthand for a larger truth about the German war effort. The Wehrmacht was not invincible. Its vaunted technical superiority was real in specific, limited contexts, but it was built on a foundation of compromises and desperation measures that undermined long-term effectiveness. The Panther could dominate a single engagement, but it could not dominate a campaign. It could win battles, but not wars. And the reason was not courage or tactics or even firepower. It was the unglamorous mechanical reality of final drives and transmission gears and the brutal arithmetic of industrial warfare. American tankers began to receive updated tactical guidance in the winter of 1944. The briefings acknowledged the Panther's strengths but emphasized its vulnerabilities. Crews were taught to observe enemy tank movements for signs of mechanical distress, Panthers that lagged behind formations, that moved hesitantly, that showed unusual exhaust smoke, or heard making excessive engine noise. These were likely tanks operating with damaged or failing final drives, tanks that could not maneuver effectively, tanks that were one engagement away from immobility. The doctrine shifted subtly. Instead of purely defensive tactics focused on survival against superior enemy armor, American tank commanders were encouraged to maneuver aggressively, to force Panthers to relocate frequently, to exploit the German tanks' mechanical fragility. The goal was to make the enemy's technical sophistication a liability rather than an asset. The Germans, for their part, were acutely aware of the problem. Captured correspondence. From tank division, commanders revealed frustration and resignation. One letter, written by a Panzer Company commander in December 1944 and recovered after the Battle of the Bulge, expressed the bitter reality. Our Panthers are magnificent when they run, but they run less each week. We began the offensive with 14 operational tanks. Today, we have 6, and only 2 of those losses were due to enemy fire. The others are scattered across Belgium and Luxembourg, broken down, abandoned. The crews are excellent, the guns are superb, but the machines betray us. I wonder if the generals who ordered these tanks ever stood in the December cold beside a Panther with a seized final drive, watching the enemy advance while our most powerful weapon sits immobile and useless. This letter, circulated among American intelligence officers, captured something essential about the final year of the war in Europe. Germany was not defeated by any single battle or campaign. It was defeated by accumulation of losses that could not be replaced, of mechanical failures that could not be repaired, of industrial capacity that could not be expanded, of resources that could not be obtained. The Panther's final drive was a microcosm of this larger collapse. Every Panther abandoned due to mechanical failure represented tons of steel that Germany could not afford to lose, hundreds of man-hours of skilled labor that could not be recovered, and a gap in the defensive line that brought the Allies one step closer to the Rhine. The testing at Aberdeen concluded in late November 1944. The captured Panther was, by that point, barely functional. Both final drives had failed, the transmission was damaged, and various other systems had broken down under the intensive testing regime. The engineers compiled their findings into a comprehensive report that ran to hundreds of pages. Copies were distributed to armored commands, to intelligence agencies, to military planners working on post-war tank development. The report's conclusions were unequivocal. The Panther was a tactical success and a strategic failure. Its design represented the apex of what could be achieved within German industrial constraints and simultaneously demonstrated the futility of attempting to overcome material disadvantages through technical sophistication alone. But the report also carried a warning for American designers. The Panther's flaws were not a reason for complacency. They were evidence that even the most advanced engineering could be undermined by fundamental design errors and insufficient resources. The Americans had won the production battle, but the next war might be different. Future enemies might have both technical sophistication and industrial capacity. The lesson of the Panther was not that German engineering was inferior, but that engineering without adequate resources, without realistic design parameters, and without proper testing would always produce beautiful machines with fatal flaws. In the decades that followed the war, the Panther acquired a mythological status among military historians and armor enthusiasts. It was remembered as one of the finest tanks of World War II, perhaps the finest, a perfect synthesis of firepower, protection, and mobility. This reputation was not entirely undeserved. On a purely technical level, the Panther represented remarkable achievement. But the mythology often omitted the mechanical reality, the staggering number of Panthers lost to breakdowns, the logistical nightmare of maintaining them, and the strategic consequences of deploying a weapon system that promised invincibility but delivered unreliability. The American engineers who tested the captured Panther understood both sides of this contradiction. They respected the vehicle's capabilities while documenting its failures. They admired the sophistication of its design while noting the hubris that had produced it. And they recognized in that failing final drive a lesson about the nature of modern warfare that transcended any single battle or weapon system. War was not decided by the quality of individual machines, but by the industrial, logistical, and human systems that sustained them. A superior tank that broke down was worse than an inferior tank that kept running. A crew with mediocre equipment but reliable supply lines would outlast a crew with excellent equipment but no spare parts. Victory went not to those who built the best weapons, but to those who built enough weapons, maintained them adequately, and kept them operational long enough to bring overwhelming force to bear. Lieutenant Fisher, who had placed his hand on that overheating final drive housing in September 1944, remained in the Army after the war. He participated in the development of America's first post-war tank designs, and he carried with him the lessons learned from the Panther. In an interview conducted in the 1960s, he reflected on those months at Aberdeen. "We thought we were just testing an enemy tank, finding its weak points so our boys could kill it more efficiently. But it became something more than that. We were learning about limitations, the limitations of what engineering can do when resources are scarce and time is short. The Germans tried to build a perfect tank and they came close. But perfection is expensive and they couldn't afford it. So they compromised and the compromise killed them. We were smarter. We didn't try for perfection. We tried for good enough, in large enough numbers, and that was what mattered." The final drive, that small, overworked, inadequately designed component, became in memory what it had been in reality. The weak link that broke the chain. It represented the point at which German ambition exceeded German capacity, where theory encountered the immovable reality of physics and metallurgy and industrial production. It was the place where the tank stopped being a symbol and became a machine, subject to the same forces and limitations as any machine, vulnerable in the ways that all complex systems are vulnerable when pushed beyond their design parameters. And for the American servicemen who had fought against Panthers in the hedgerows of Normandy, in the forests of the Ardennes, in the final desperate battles along the Rhine, the knowledge that their enemy's most fearsome weapon was undermined by mechanical fragility provided a kind of retrospective comfort. The men who had died fighting Panthers had not died facing invincible demons. They had died fighting machines that, for all their sophistication and power, were still just machines, capable of breaking, prone to failure, and ultimately defeated not by superior virtue or courage, but by the patient, grinding arithmetic of industrial war. The captured Panther at Aberdeen was eventually cut up for scrap, its metal recycled, its components catalogued and stored in archives. But the knowledge it had yielded persisted. It influenced American tank design for decades. It shaped tactical doctrine and strategic planning. It became a case study taught at military academies, an example of how technological superiority could be negated by fundamental design flaws and inadequate industrial support. The final drive of that specific tank, ground down, overheated, and ultimately destroyed by testing, had served its final purpose. It had revealed a truth. That truth echoed through the decades, that modern war is won not by heroes or by machines, but by systems. The system that could produce reliable equipment, deliver it to the front, supply it adequately, repair it efficiently, and replace it when necessary, would triumph over the system that produced fewer, more sophisticated weapons that broke down in the field. The Panther was a magnificent machine, but it was part of a failing system. The Sherman was an adequate machine, but it was part of a functioning system, and in total war, the system always defeats the machine. The final drive, in the end, was more than a component. It was a symbol of the gap between aspiration and reality, between what Germany needed its tanks to be and what its industrial base could actually sustain. It was the point where engineering became philosophy, where metal and gears encoded the larger truths about resource constraints and strategic overreach and the ultimate futility of trying to compensate for material disadvantage through technical excellence alone. The American engineers who discovered this weakness, who documented it with such care, who traced the cracks and measured the wear and calculated the inevitable failure, were doing more than technical work. They were reading the physical evidence of an empire's collapse, inscribed in metallurgical stress patterns and gear tooth wear. They were seeing, in that failing final drive, the larger failure of a system that had sent its soldiers to war in machines designed beyond the capacity of the nation to support them. And they understood, even if they did not always articulate it, that the same fate could befall any nation that prioritized technological sophistication over industrial sustainability, that valued individual weapon performance over systemic reliability, that believed superiority could substitute for sufficiency. The lesson of the Panther's final drive was not about tanks. It was about the relationship between means and ends, between capability and capacity, between what can be built and what can be maintained. That lesson, purchased with the lives of soldiers on both sides, inscribed in the broken gears of a captured tank, documented in hundreds of pages of engineering reports, remains. It speaks across the decades, a reminder that in war, as in all human endeavors, the spectacular often fails while the sufficient endures. The Panther was spectacular. The Sherman was sufficient. And sufficiency, multiplied by industrial abundance and sustained by logistical competence, proved to be the arithmetic of victory. The final drive was the weak link, and in that weakness lay a truth larger than any single battle, any single tank, any single war. That strength without sustainability is merely a different kind of weakness, and that the nations which understand this difference will inherit the future from those who do not.